good evening to each and one of you present today. I am Varna. Welcome to day 3 of this webinar. On behalf of Space Advancement and Research Cell, I offer my regards to all the excited attendees for joining us today. Today's schedule is an interesting session by Dr. Rudy, who will be speaking on green propellants.
Now, before we begin, I would like to give you a small introduction about Dr. Rudy Gostowski. Dr. Rudy is an ex-NASA scientist, a respected educator, and a former mentor for students. After completing a doctoral program in chemistry at Southern Illinois University, he became a tenured professor at Austin Peay State University, where he taught analytical chemistry and researched organic radicals with undergraduate students as fellow investigators.
Today's presentations are devoted to an overview of green propulsion and its important aspects. I wish this conference enlightens us all and provides us with approaches to deal with the problems of tomorrow.
Now, as we begin, I'll request our honorable chief guest, Dr. Rudy Gostowski, to begin today's concourse. Please, sir.
And good morning. I need to turn on my camera. Oh, there we go. Okay, I got my camera on. I assume you can hear me. You're smiling, so
Yep.
it must be working. So good morning, everyone.
Good morning.
Oh, well, good evening to you. I'm sorry, I forget. Anyway,
It's a good morning for you and a good evening for us.
there you are. There you are. Or as my one of my very good student and friend would be saying here, Buenos dias, and Buenos noches in your case. So he's Spanish or Hispanic from Mexico. At any rate, I'll go ahead and get started then, I guess. So I'm going to be sharing my screen here with you. So, okay, we'll just go here. And then we'll get on with this. I need to move this to my other screen so I can see it. Oh, come on. There we are. Okay. And away we go. Oh, I will not be able to see it. Well, when I need that information, I'll go to it. So anyway, today what I'll be speaking on is the pursuit of green space energy. I wanted to say energy rather than just propellants because these materials could be used for surface energy also to operate any sort of mechanical device that requires power to move around. In fact, when I was working in hydrogen peroxide, I was invited to a DARPA project where they were building a exoskeleton for soldiers to wear that would increase their mechanical abilities. And they were going to use the steam generated from hydrogen peroxide to operate the pneumatic arms and legs for this exoskeleton. And I just thought that was a very interesting application. I don't know what happened with that, but at any rate, I thought it was interesting. So when we think of any kind of propellant, we're going to first move to the performance of that. And that, especially with an engineer, and if they're not thinking about the impacts to the environment or to the people using that propellant, then they may only be thinking of things like specific impulse or energy density. Energy density being the idea that you want a more dense material so as to reduce the frontal area of the rocket and therefore reduce the drag. Hypoglycity, where that you want a propellant in a bipropellant mode to ignite spontaneously on contact. And that was discussed on Friday's presentation. And the name of the gentleman escapes me right now. I'm sorry, I apologize to you. But you were talking about that. And then storability is important, even though we have used non-storable cryogenic propellants. They do produce a challenge. We know that when the space shuttle was on the pad approaching launch, they would be continually topping off the cryogenic tanks, trying to maximize the amount of the propellants, the liquid hydrogen and liquid oxygen that we have present. without overpressurizing the tanks. And of course, that would be a challenging thing to do, to maintain that pressure within the operating specifications of the tank. The thing about when we're seeking performance is it can be unforgiving. If we mess up, we can kill people, or we can seriously damage the environment. And so I have the skull and crossed, and the on the other side, the right side, that's dinitrogen tetroxide boiling off, producing those orange fumes there, which are quite toxic. And so things such as hydrazine as a monopropellant, or hydrazine in combination with dinitrogen tetroxide as a hypergallic bipropellant, hydrazine with fuming nitric acid as a hypergallic bipropellant. And then probably the winner of the show, best in show for the most toxic combination and most dangerous combination would be lithium, hydrogen, and fluorine as a hypergallic tripropellant, producing the highest possible theoretical ISP of 542. So if we're just thinking about that performance number, we'll neglect these other things. And so that's why I'm talking about this today. So we have to make trade-offs in any selection. We have to do a trade study. We cannot have it all. And in spite of one of the NASA administrators from, I don't know, 4 administrators, 5 administrators back, who said we could do everything at the same time. We could be faster, we could be cheaper, we could have higher performance, all at the same time, but it's impossible. And the man, he was an engineer, and he knew better. It was politically expedient to say something like that. So if you're going to have performance, you're going to impact your handling safety, your environmental impact. If we consider the environmental impact, we may have to accept a lower performance. We cannot have all of these. There will be a trade study, a trade-off. So what's the holy grail of green propellants? Well, we would say, okay, it's hydrogen and oxygen. We're producing water. How much more innocuous could it be to make water? And we get a fabulous ISP, actually the highest ISP that we've actually used of 450 seconds. However, liquid hydrogen, liquid oxygen have their own challenges. They are not as dense as we would like. They're cryogenic, and they give us tremendous technical challenges. They combust at a very high temperature. And I'm also going to talk about what I'm going to call pseudo-green propellants. And that is, these are not really green. They are going to pollute. They do not produce the handling considerations of some of these things, such as hydrazine and dinitrogen tetroxide, but they do pollute. So I'll call that pseudo-green. It's not really green, but we're going to still talk about that. Or to have a quote here, you must break a few eggs to make an omelet. We're going to have to do some things to get a certain amount of performance. So what are our options? Well, here's a list that I put together. I'm sure that I have omitted something. I'm sure those will come up in the questions, and maybe I'll have an answer. I don't know. Hydrogen peroxide as a monopropellant does not perform real well, but it has been used in many vehicles. And we'll see that a little bit later on. But it only has an ISP of 117 seconds. So it's a low performer. Nitrous oxide is a better performer, but unfortunately associated with nitrous oxide, many people think that it's totally safe, that you can do anything you want with it. In fact, automobile enthusiasts or motorcycle enthusiasts will install a nitrous oxide tank in their vehicle, hide it away, have a secret switch. They turn the switch on, and all of a sudden their engine, its performance is doubled. Of course, it's probably going to destroy the engine eventually, but it will increase their performance momentarily. The hobby rocketry people use nitrous oxide, but there is some possible dangers in there when you scale up. The Spaceship One uses nitrous oxide, and they had a major accident when they were doing some ground testing, and it was partly the technicians were not following the safety protocol, and then the engineers had not considered the consequences of their design. And we were involved in that investigation. I probably should say no more on the risk of being sued by Sir Branson. Another green option would be the Han propellant, monopropellant, hydroxamine nitrate, and it has a great ISP at 260 because it's essentially a bipropellant that's together. And the problem that we're going to get into there, and also with the ADN monopropellant, ammonium dinitride, dinitroamine, amide, I'm sorry, I'm butchering my organic chemistry for me the morning. The problem with either of these is that they combust at a very high temperature, and a catalyst is required for their ignition. And it's very difficult, very challenging to find a catalyst support that can sustain that high temperature for any time. And that was something I was working on for these propellants when I was at NASA. And we weren't getting a whole lot of traction in doing that. It's difficult. And then the hydrogen oxygen bipropellant, you know, the holy grail of green propellants. As far as pseudo green options, we can burn HTBP, which is what you have in many solid engines, and we can have a hybrid with either hydrogen peroxide or nitrous oxide. Those are good performers at 240, 250 seconds. My favorite bipropellant, I think, is kerosene with hydrogen peroxide. I found a number for 85% peroxide. It would be higher if we went up to 98% hydrogen peroxide. So I don't know how high it would go. I could not find that number readily. But it's 258 with 85%. And then the kerosene oxygen bipropellant as used in SpaceX. So I'm going to spend most of my time, in fact, I'm really going to spend the bulk of my time now that's remaining, talking about hydrogen peroxide, because that's what I've had the most personal experience, and that's what I think is a good place to go for people like yourselves that are wanting to have a sounding rocket, for us that want to have a sounding rocket. I think it's a practical way to go. I believe it is attainable for us to build hydrogen peroxide with kerosene bipropellant engine, maybe starting like what we're doing with a hydrogen peroxide thruster and gradually working our way into it, because it's a challenge to even make the thruster. We have to do that correctly. Some relevant characteristics of hydrogen peroxide: decomposes to oxygen and water, so it's not going to have any environmental impact, and it's not going to be toxic to the people that are handling it. Once it's decomposed. Now, you certainly do not want to drink hydrogen peroxide. You know, that would certainly kill you. And it does have some handling considerations that we'll talk about a little bit later on. But we're getting in that decomposition, it's exothermic by 196 kilojoules per mole. And we can accelerate the rate at which hydrogen peroxide decomposes with different things such as metals, elevated temperature. So once we get something started, it's going to be self-sustaining because of the heat. In fact, that becomes a concern because of heat soaked back into the piping to the engine. It could cause a problem at a valve or at a tank that's upstream from the device. And then surface morphology. Is the surface smooth, which would be not accelerating, or is it ripply? Is it rough? That would cause accelerated decomposition. And we're going to be referring to hydrogen peroxide at a higher concentration as HTP from here on. So that stands for, and it was adopted many years ago, back in the 40s, meaning high test peroxide. Now, peroxide, as it's purchased, will have stabilizers in it to mitigate a metallic contamination causing it to prematurely decompose. However, many times we don't want that when we're using it as propellant, and we'll have to remove those stabilizers. There's a way to do it. I've done it. I still have all my fingers, so things seem to have worked out okay. I never had an accident. There is some hazard to it, so a person has to proceed carefully. And then what I have heard recently in some of the research from Poland is that the stabilizers did not affect the catalyst, so they were able to leave the stabilizers in their case. So perhaps that'll work. I don't have personal knowledge of that. Catalyst for decomposition of peroxide, certain pure metals. We could plate the metal into another supporting metal. We could have it supported on a ceramic. And I say here it's poisoned by stabilizers. This was prepared. I'm using some slides from my past. That it used to be, we said that it would be poisoned by stabilizers. It may not, in fact, be true. The advantages of peroxide: safer handling, much safer. We don't have a cryogen. We don't have to be concerned about having a frostbite burn to our hands if we were to pour it on us. There's no cryogenic requirements. You don't have to worry about boil off. The decomposition products are totally safe. You can have a smaller vehicle because of a lean burn mixture. You have cooler combustion than many combinations. Hybrid engines are more stable with peroxide than using LOX, and it's pretty cheap. You know, you can buy peroxide at a 35% concentration level, and then you can increase its concentration by removing the water. It's not a difficult thing to do. It's dangerous, but it's not difficult to do. So some of the applications of peroxide, we've already talked about monopropellant thruster, where the peroxide encounters a catalyst, producing steam and gaseous oxygen and giving you your impulse for your rocket. Or you have a bipropellant or a hybrid mode where we're using the gaseous oxygen to burn with a fuel. That fuel could be a liquid or it could be a solid in the case of a hybrid. And the steam can actually cause the combustion event to occur if we hold that, if we have a flame holder present in our engine. So it's a heritage propellant, meaning it's been used many times. It was the initial liquid propellant. It was what was used by von Braun in Germany. So it was used in the X-1, the X-15, in their reaction control systems, the Mercury capsule, Soyuz capsule, Progress, all these different rockets and capsules and rocket planes used it to control the attitude of the rocket plane or whatever it was. It was used as a liquid bipropellant in the British Black Knight project, the AR-2, the LR-40, that was in Russia. It's been used in hybrid. There was a large hybrid rocket using peroxide by General Electric. It's been used to run turbopumps in the V2 and other rockets. It's been used in torpedoes, submarines, the JO pack that we attach to an aircraft so that it could take off on a short runway. What I'm going to talk about now is the X-37 project. I was involved in X-37. Besides my work with the shuttle boosters, my other major project for NASA in the beginning was the X-37. And we worked on that for several years. Excuse me, I'm going to grab a drink real quick. If you want me to talk about roasting coffee, I can do that sometime too. Anyway, this is a picture schematic of the X-37, or what was also called the Orbital Test Vehicle. And it was a reusable space technology demonstrator. And it was going to use hydrogen peroxide and kerosene combination in a bipropellant engine. And you see the peroxide tank here in blue, and the kerosene or the JP8 fuel tank in the front here. It's going to have a cargo bay. It was an autonomous vehicle. There was no astronaut inside here. And the concept was to put it in the shuttle bay, fly it up, and then release it and fly it back to Earth using that bipropellant engine. And as soon as I saw this, I thought, this may not be such a great idea, because the proposed location in the cargo bay presented an extreme risk to the astronauts in the shuttle and was eventually abandoned following safety assessments. And I was partly responsible for that, along with a gentleman named Alvin Edson at Marshall Space Flight Center. Now, the first build of the X-37 is pictured here. You can see that it's following the space shuttle flying boat concept or lifting body concept. We transferred it to the Air Force in 2002. And after that time, it was launched on a Boeing Atlas and then on a SpaceX Falcon booster. The Air Force has done various things with it. They won't talk about everything they've done. They've been accused of using it for all sorts of things, and we just don't know. So now I want to talk about material compatibility. That's what I did mostly, was look at the compatibility between peroxide and the materials that are used in the propulsion system, because this is going to affect performance and safety and that sort of thing. So prior to NASA doing this, there was use recommendations that came from the 1940s and 50s. And the recommendation was to use what was called Class 1 or Class 2 materials, which would be glass. You can't use that in the propulsion system. Or use alloys of aluminum, such as 52, 54, 60, 61. Those are commonly attainable. You could use stainless 316, or I mean, the stainless, well, the 300 series, so like 316. Teflon is fine. The other things were to avoid contamination, gross and otherwise, because if it's even lower contamination, it will eventually cause a problem. You can add stabilizers, but it may have problems, and provide proper venting and pressure release should you have an overpressure event. And this rating system is given here as to how this worked. Class 1 materials are highly compatible, can be used for long-term storage. So if I were to go back, that would be something like glass and pure aluminum, not an alloy, but pure aluminum would be a Class 1. Then Class 2 materials are satisfactory for short-term contact. So that could be in your tankage and piping in the vehicle. So we can have it loaded for 1 week at ambient temperature and be okay. And then materials for short-term contact, that might be in the actual engine where it's only going to see that for a brief time. And then Class 4 would not be recommended in any case because those are essentially catalytic materials. When we talk about incompatibility, we're looking at the interface in this Venn diagram between the peroxide and the material. And we're just concerned with what's going to go on here. And it could result in either an alteration of the peroxide, in other words, the fluid, or it could cause an alteration in the material that's contacting it, or it could cause a reaction between the two, causing an overpressure event or a temperature rise. So we need to understand compatibility at all the levels, at the molecular level, the level of a sample coupon of the material. Then we need to consider what's going to happen in our component, say a valve or a piece of tubing or something like that, a temperature sensor, all those sorts of things. I've been stewing over that some on what we're doing right now at the school as far as compatibility with temperature sensors and pressure sensors. Because it's difficult to find something that's going to be workable. And then we have to look at the entire system. We put the entire system together. We load it with peroxide. We monitor the temperature. We have no intention of firing the propulsion system at that time. We're just looking to see, does the pressure go up in and of itself without the peroxide encountering a catalyst? So we need to make sure that all of that is working correctly. So ways of increasing compatibility. Surface treatment. This was discussed on Friday in reference to dinitrogen tetroxide. It would also apply to fuming nitric acid. First thing would be to make sure everything's clean so that we are removing our gross contamination. That would be something as simple as using a detergent, a surfactant, to remove any oily organic material. Organic material is extremely concerning. Definitely do not want anything that came from the machining of the part to still be present whenever it's going to see peroxide. That would definitely cause a problem. And then the next thing is what's called passivation, where we produce a surface oxidation layer on that particular part. So we expose it initially to nitric acid, where the nitric acid is causing some oxidation on the surface, and then we expose it to gradually increasing concentrations of peroxide, starting at like 10% and going through 30%, 50%, all the way up to whatever is the use concentration of the peroxide. So if we're going to use 90%, we want to finally expose it to 90%, and we observe it to see, are we forming bubbles? Is the temperature rising? If that's not happening, we've created a passivation layer and everything is okay. Now, if we want to spend money, because what I've said so far doesn't really cost much. We can certainly clean it with soap and water. We can apply our nitric acid or peroxide. That doesn't really cost much. But there's something called electropolish, where we use electrochemical removal of impurities and producing that oxidation layer. I never felt this was necessary, and I think it was really just some people trying to ride on the popularity of peroxide at that particular point in time. I could be wrong. We could apply coatings. We wouldn't be applying coatings to a metal component, but if we're going to be using, say, fiber composites for our tankage, we could try to apply a coating. However, that's very risky. That could result in a serious problem. Certainly couldn't use it on a man-rated vehicle. But if we're trying to minimize our weight while having sufficient margin in our acceptable pressures, then we could do this, and we could apply a metallic coating to the inside of a carbon fiber tank, and it might work. I have an associate at Marshall Space Flight Center who that was his thing. He was doing this. I've seen what he did with it, and apparently it was working. So I don't know. We'll see. But if you do have a breach of that coating, and the peroxide comes through just the smallest hole, then it's going to spread then at a perpendicular to where the peroxide is coming in, and it'll start eating it'll start destroying, it'll start oxidizing the resin in the fiber composite, and we'll destroy the tank, and we'll lose mechanical stability and probably lose the whole thing, the vehicle and everything. So here's some of our crew safety and mission success concerns with peroxide, because it's always a trade-off. There is no perfectly safe propulsion system. Well, electric propulsion, from what we saw, is safe, but you can't get the orbit that way. Have a vapor phase explosion, compressive detonation. That sounds terrible, right? Excessive pressure and temperature rise within the system during your mission. You can lose mechanical properties such as strength, elasticity. Can have components swelling when they're exposed to peroxide. And then you could have flammability concerns and impact sensitivity. In other words, if we strike that metal, is it going to start an ignition event? So one way that we assessed compatibility was with a calorimeter. This particular calorimeter is called an isothermal microcalorimeter. You can see here the device. The samples went in these 4 cavities, and then we had a stir to keep, there was a water bath in here to keep the temperature homogeneous through there. The sample would go into one of these vials. This was used to be able to hook onto, to lower these down into the chamber or to remove them. And we put the vial in a thermostated water bath. The heat flow is measured by a Peltier device. It's calibrated to resistance heaters. And we compare a sample vial to something of similar thermal mass, because the whole measurement that we're taking is a comparison. And then we can do this kind of conversion where we take the watts, convert it into joules per second. So now we're into a rate. Then we're looking at moles per second. Now we're definitely into the kinetic domain. And then we can get into the engineering domain of pressure per second, pressure rise per second because of decomposition. So this is your typical data here. So I've got energy on the y-axis, and this is the watts, and of course we would have to do the conversions to get to pressure. On the x-axis we have time, and for compatible materials such as this A286, nickel 200, and the Crest 347, they were pretty compatible. You can see these are approaching flatline, especially A286, where Inconel was really terrible. And this is the typical results that we were getting. Another way to measure compatibilities with gas evolution, where we're deliberately causing the peroxide to decompose, and then we're seeing, well, how fast do we accelerate the decomposition by putting in a sample coupon of the material that we want to investigate. So we have that sample coupon inside a vial containing peroxide, have a Teflon tube that's going over through a water bath into an inverted burette. And we're displacing water. You've probably done this in a general chemistry lab when you were taking your chemistry classes, where you're displacing the water inside this glass tube or burette, and we could then measure how much we've accumulated. And then actually doing this over an extended time, when you get to a certain level of oxygen in here, you would then open this to vent it so you could start the process over again. The sample vial, as I said, was in an oven. The gases displaced the water in the burette, and then the gas volume was recorded at regular intervals. So this was a great project for a student. I had an intern that was doing this over the summer, and then I loaned all the equipment to her and her chemistry professor back at her school, and she went back there and did those experiments. They presented this at a conference, had a paper from it, and she went on to working at Marshall Space Flight Center after she graduated. And then a final way here, although there's certainly other ways, is what's called a heated bath. In this case, we have peroxide of a known concentration in the vials, and then we put samples in some of the vials. Those vials were passivated. They have a vented top. You can even see the hole here where they're vented. At regular intervals, we measured the concentration of the peroxide that was there, and the changing concentrations converted to evolved gas. So we're converting peroxide into oxygen and also into water, and then we could do a stoichiometric calculation from that, and then the evolved gas is presented as the loss of oxygen from the hydrogen peroxide, which that has a accepted term for. It's called active oxygen loss, or AOL. And here is a chart of AOL taken from this sort of data, where we have different alloys of aluminum. This is a Teflon-like material. That's a stainless there, 316. Here's 316 that was welded. I wanted to look and see how much welding changes the compatibility. You can see here very quickly that this is decomposing a lot faster because of the simple thing of having a weld. I took samples of 316 stainless steel to a welder technician at Marshall, and he put welds in there, and then we cut them up into coupons and measured it. And I have a paper on that, and we speculate as to why it happened. It changes the initially homogeneous depositions of the crystals in the alloy into making them maybe more concentrated at the surface, and exposing less compatible parts of that steel alloy. So moving on from here. Oh yeah, these are still class 1, class 2 materials. And as you can see, the aluminum and this particular Teflon are the only class 1s. The 316 approaches being class 1, and I consider it to be good enough. We just can't weld it. We have to find other ways of joining them besides welding. Now, we can take those 3 ways of measuring compatibility, and we can see, do they agree with each other? Do we get the same result, whether we do a bath test or a gas evolution test or an isothermal microcalorimetry test? And if we convert to common units, do we get the same compatibility? And we should, no matter how we measure it. Here's some publications. I'm going to make this presentation available to you if you want to go look for these. And I'm not going to spend any time with that. So now I want to move on to hypergolic hydrogen peroxide, because initially it was thought that the only way to use peroxide really was to figure out how to make it hypergolic. Now, since that time, the discoveries have been made, especially by a research group in Korea, that you don't really need it to be made hypergolic, that you can just use the heat from the decomposition of the peroxide to cause the ignition to begin. So it's not really necessary, but we did some work on it. I want to share that with you. Now, this is a picture of myself and two other people measuring ignition delay. And this is a lab scale experiment. We were doing this to support what was going to be the test of a full-on engine test. The project manager lacked patience. He wanted to go ahead with his test, and he blew it up. It was a big fire. Pieces of the engine went everywhere because he did not want to wait on our results. And what happened was when they started pumping in the peroxide and the propellant, or the fuel, it did not ignite initially, and it accumulated in the engine. What they call pooling. It was making a pool of the two parts, and then it ignited and it blew up. But anyway, the lab scale experiment. Ignition delay is considered the time until ignition, and it's measured for potentially hypergolic propellant mixtures. And while perfect scale up to a bipropellant engine is not possible, we can't take the time delay for our experiment and say this would be the same time delay in an engine. The relative ranking of the different combinations should be applicable. Now, it might not work out perfectly because that's always the case in scaling up from a lab scale experiment to a full-on experiment. So we don't always know. That's why we have to still do the test. Even with modeling, you always have to go ahead and test. But anyway, because of differences in mixing and heat transfer, we could not directly relate one to the other, but the relative order of delay times is expected to be the same. So many combinations were tested. And we started out with dimethylhydrazine and dinitrogen tetroxide to use as a baseline because people already know in the engines what is the ignition delay. So we could then somehow approximately come up with a multiplier and maybe make those comparable. So we were looking at fuels that were amines, and those were blended with a cobalt catalyst and made this purple fuel. And anyway, that's what I'm going to show you some pictures of here in a moment. So this is the setup for it. During the initial test, it was determined that dropping the peroxide into a container of the fuel gave you the most consistent reproducible results. So a high-speed camera was triggered by a syringe pump. So here is our syringe pump, and it's pushing the plunger of a syringe forward. And then that is then dropping the hydrogen peroxide down into a quartz cuvette that contained then our fuel. We have our slow motion camera here that was collecting data. We have an exhaust here to get rid of our toxic fumes, especially the hydrazine and nitrogen tetroxide was certainly hazardous. I've handled that stuff. It is bad, very dangerous. But anyway, the camera was activated by when the syringe pump came on. The syringe pump was remotely activated from a computer. And the syringe pump yielded consistent drop size. So the drops that were going into the quartz cuvette were pretty close to being the same size. And that's essentially how it would work. And you can see over here, this picture was staged for this photograph. It did not make such a flame. We deliberately pumped in a lot of stuff really fast just to make a good picture. It's not the way we really did the experiments. They weren't that dramatic. But now I'm going to do my own version of the slow motion. I'm taking slides that are occurring at the various time intervals, and I'm just going to advance them, and you'll be able to see then what's happening. So you can see the drop has left the tip of the needle. So there's the needle, there's the drop, the fuel is down here. The fuel is, the vapor pressure is causing the fuel to rise up the sides of the cuvette, and then it's condensing and coming back down. So that's what this is. And here we go. So that would have been a combustion event. And then to take it back to where we would take our times, at the point where the drop impinged on the fuel, that is time 0. We then continue on. You can see that there's some reaction happening. We would take either that slide or this slide to say this is the beginning of a reaction. You can see some vaporization occurring. And then this point right here, oh, wait a minute, I think it was actually, yeah, I guess this was always hard to say. My colleague made the call on exactly when the ignition event was. I mean, certainly there's an ignition here. So I guess this would have been where we would have said you have the flame kernel beginning. And of course, there it's definitely going. And here's all those slides on one sheet here. So you can see again, the drop is time 0. The beginning of the reaction is somewhere between 6 and 7 milliseconds. And then we would say the flame kernel was at 13 milliseconds. So we'd say that the ignition delay time was 13 milliseconds in our experiment. And I've got the same information over here. And anyway, that's the way that experiment went. And then there's a publication of that. The person that was running the entire project was John Blevins. He is currently the lead on the development of the, oh boy, now I won't be able to think of what it's supposed to be called, the propulsion system for the Artemis project, the return to the moon. He is the lead. So now I want to talk about the robotic lunar lander. I did not exactly work on this. I was consulting because by this time I was no longer working for the agency. I had already moved to the college, but I came down at the invitation of Alvin Edson, the safety guy, because he wanted me to look at what they were doing and he wanted to discuss, is this going to be okay? So here is this thing. So this is actually much smaller than this picture would have you think. It's the size roughly of, it's probably maybe a meter long, but not, I think it's probably not quite that much. I think it might be 2/3 of a meter or something. But anyway, it flies autonomously. It's robotic. You have a central hydrogen peroxide monopropellant thruster that is offsetting gravity, so as to simulate a lunar environment where you would not have that gravity. And then you have smaller hydrogen peroxide monopropellant thrusters that allowed the lander to hover and to maneuver around. And these are peroxide tanks. And I had not really noticed this before. These are fiber composite peroxide tanks. So apparently the guy that I used to work with talked him into using these things, because that is what we're seeing here. And then the post-test processing, which was my part in the discussion, was that they would flush it all out with deionized water and then use dry nitrogen to dry the system out before they would put it away. Because we did not want any peroxide hiding in the system someplace, causing corrosion and possibly a unwanted decomposition event. So now I'm going to go into what we've been doing at Triton Fisk, the thruster development there. And this will be a few slides, but I hope you will let me know if I'm going way over time, because I've not been noticing. So this was part of the NASA MINDS program, which is the Minority University Research and Education Project, or MURAP. This is in the Office of Education at headquarters. I knew the former director for MURAP. And so they're taking that as the M of the MINDS, and then the rest of it, Innovative New Designs for Space. And I'm going to go through all this stuff here. I'm not going to talk about this. You can read this. It's just mainly going to minority serving institutions to give them an opportunity to work on a relevant project. And so at the schools, we had design teams working on the 3 parts of the thruster, the nozzle, catalyst pack, and the test stand interface. So we had a team at Triton, a team at Fisk, and those are the various people. And I won't go through all the names because you don't know these people. And then here are our mentors. I just want to give them some credit, especially Michelle Harton. She's a MIT graduate, electrical engineer, went on to be a math teacher because she wanted to do something that she felt was more meaningful, and I hope she will continue working with us. And Steve Rogers was my boss at Marshall Space Flight Center in the propulsion lab. He later worked for ATK Thiokol. He's currently retired, but not really retired. He's retired in the sense I'm retired. He still works all the time. Matt Canella was a propulsion academy graduate whenever I was the coordinator. He now works for Ball Aerospace, and he's currently involved in the propulsion system to get the solar sail out to the sun so as to then be able to deploy it and fly it back from there. And Sarah is our lab coordinator for chemistry at the college. And Vanavak Desh is a aerospace engineering student in Montreal, and he's developed some code to design nozzles. And so he was helping us some, but he was very busy working on his graduate thesis. So he was limited on what he could do. So the Artemis program, there's all this verbiage here, and I'm not going to go through all this stuff, but just we're supposed to land the first woman and the next male on the moon's south pole by 2024. This is not going to happen. There's no way it's going to happen. But that's what their goal was. This throws back to President. I really have a hard time saying this. President Trump. Anyway, this political theater is what they would call it, because this is impossible to do. But anyway, they're hoping to find and use water and resources for future missions. Now, we can get to the moon, but it's not going to happen that quick. It really is going to depend on how fast Elon Musk can get there, I think, unless China or someone else does it first. The objectives, though, was, well, this is our objectives for our team. From here on out, this is what we're doing, not what the program was saying that we should be doing. So in keeping with the Artemis program goal of in situ resource utilization, we wanted to use water to make our peroxide. That's essentially where we were going. We wanted to use lunar and Martian water to make hydrogen peroxide. And I had found where we could possibly use solar energy to do that. And so our first milestone in doing that is to develop our own thruster that we could then test peroxide in. And so what Dr. Rogers, I was mentioning earlier, Steve Rogers, pointed out to me, well, for this to be feasible, can you get enough ISP to use this? And so we did a little looking and saw that hydrogen peroxide with kerosene, 258 seconds. And it's comparable to other room temperature liquids like nitrogen tetroxide and aerosine combination. That's basically kerosene of the lunar ascent module. And it's going to be easier to get off the surface of Mars than to get off the surface of the moon. So it would probably work. So now we needed an inspiration. Because you remember when I was talking on Friday, a big problem or a challenge, not a problem, a challenge in pursuing this as a career is being creative. And I'll admit I'm not creative. Partly because I don't possess the knowledge in all the areas that I should have. I've got some knowledge in engineering, but most of it is in chemistry. So I found this article by Joe An, Kim, and Yoon and Kwan, I guess, from Republic of Korea. And they came up with a very clever design for a bipropellant hydrogen peroxide engine, where they're bringing the fuel, the kerosene, up this tube, and then it distributes from the center outward and comes out of these orifices here. And then in this area here is the catalyst, and the peroxide's coming in here, and then it's decomposing, making high temperature steam, so that when the oxygen with the high temperature steam encounters the kerosene, it ignites. and then we have a combustion chamber. So clever idea. So our design was inspired by that. And the integrated oxidizer distributor plate and fuel injector is a unique configuration. I've never seen this before. They've gone on to do some other things where they're trying to throttle it in a way that's different than the normal throttling. But I won't go with that. I haven't read the article completely. But our implementation of this design inspiration was to not include the fuel injector because we're not making a bipropellant engine, we're making a monopropellant thruster. But our long-term plans are to then eventually make a bipropellant engine, and so this makes this into a something that we can convert the thruster into the engine by changing this bulkhead plate and by adding on the combustion chamber. So that's why we did this. So here's a conceptual drawing of the thruster, and it's not drawn to scale. It would be connected to a test stand, which is not shown, and the temperature and pressure probes are not shown either. And this is this here. So we'd be bringing in the hydrogen peroxide here in the middle section, which the diameter would actually be larger. I have a transparent tube inside here so you can see it. And then we have compression bolts that pulls the bulkheads together. And then, we have our nozzle out here. And when I was talking about design teams, you can see how that corresponds to the nozzle and catalyst pack and test stand interface that the teams were working on. Here is the nozzle. This was 3D printed. And here is a version with a longer catalyst pack. So we put together a spreadsheet using a static condition to try to estimate the pressure. Found that really did not work well, so we wound up scrapping that and just using what other people have already found to be a typical pressure. We could estimate temperature from it, and that did agree with what other people were seeing as a likely temperature. So catalyst pressure or catalyst pack requirements and concerns. Besides containing the pressure of the steam and the oxygen at about 300 psi, it's got to be able to tolerate a temperature of around 1,000 Kelvin. And we need to allow close packing of the catalyst pellets. Catalyst pellets, I don't know if you can see these, but this is, we're using zeolite to simulate the catalyst. That's not what we'll actually be using. We'll be using alumina pellets, and it would have magnesium oxide on there as our catalytic material. But what we want to have is a tortuous flow path so that the hydrogen peroxide will have sufficient residence time in order to have the opportunity to completely decompose. So significant concern in design is to avoid catalyst channeling. This is where the flow of the peroxide would make a straight path through the catalyst pack and not be in there long enough to totally decompose. So to mitigate that tendency, we were adding a barrier near the propellant inlet, and that's going to be referred to as a flow restriction disc, which is in this picture. So that when the peroxide comes in from the inlet, it would pass through some layers of catalyst, but then it would encounter a disc that would, the path would have to go perpendicular to the initial flow, and then hopefully it would distribute from there. Now that's one possible way of doing this. We could go with multiple inlets. There's other ways we could maybe handle this. But anyways, something does have to be done to try to create that tortuous path, increase residence time. So we did some trade studies on the materials we were going to use for the decomposition. Catalyst, manganese oxide certainly won out. It's not as effective as silver or platinum, but it's very robust and it's very cheap. So those are important to us. We do not want to buy silver and platinum. It's too expensive. Then we were doing something similar for our chamber materials, although we only looked at stainless steel, so not a really valid trade study. Then we did a trade study on the retainer screens, because we have to keep the catalyst pellets from exiting out one of the plates, and I don't have one here. I should have. Excuse me. No, I don't have one, so sorry. Anyway, we don't want the catalyst getting out of the holes. I can go back to that picture, though. I'm talking about these holes here. We do not want the catalyst pushing through that or pushing through here. So we had to block that, and that was blocked with a screen-like material. So what do we use for a screen? Well, we're initially going to be using stainless steel, but an interesting idea is to use manganese screen, because we'll have an oxidation layer on the screen, which would make the screen serve as a catalyst also. So it's scoring higher in our trade study. Now, the highest score was for the silver, but its robustness is so poor, and the safety concerns that you would have present would exclude that from serious consideration. And platinum is just too expensive. So some other things that we were thinking about, safety concerns and mitigations, besides maintaining an adequate design margin with respect to pressure and temperature, and induced stress in the chamber wall, heat soak back, resulting explosive autocatalytic decomposition must be considered. And we're talking about premature decomposition, mitigations to avoid those things. Use a 1.5 design margin for the pressure, and then let's see what else. Going to have a default to closed poppet valve where the propellant's coming in. So the valve out here would be a poppet valve that if we lost control voltage, it would close. And then there'll also be a main propellant valve that we could shut down also. And all wetted material is going to be considered for compatibility and should be a class 1 or class 2 material. Probably can't do class 1, probably be class 2. So the nozzle design process. But before I go into this, what we're actually going to do is just produce the catalyst pack like this without a nozzle. Oh, I should have shown you. There you go. There's the holes for where the steam and oxygen is coming out. We want to build this first and test it and have this totally open so as to not have any concerns with overpressurization. And then we'll gradually block this off and try to get a good estimate of what is our pressure inside the catalyst pack. And then when we really know what the pressure is, we can design the nozzle better, because we have to design it to that. Because in this version of it, we're saying, okay, the chamber pressure is 300. We have to couple it to atmospheric pressure. And also along with that, we're accelerating the particles to produce the thrust. Okay, so there was 2 approaches taken. Proful at Fisk University was using first principles, and at Triton we were using a black box MATLAB application that was written by Vinayak Desh, and turned out it did not work for us. Now, he was too busy with his graduate work to look at what we were doing to help us understand why it wasn't working. So we'll go back and revisit that. But here is the first principles approach. This was from Mr. Profil at Fisk. And I'm not going to go through all this stuff. I don't really understand it that well. So I'll just leave it to you folks that want to read through all of this. But this is what it resulted in: a 2-dimensional sketch of our nozzle, assuming 300 psi, going to atmospheric pressure. And so it's just 1/2 of the nozzle 2-dimensional drawing. We could then rotate around that, producing a 3-dimensional object, which is what we're seeing here and what you're seeing here. And then moving on from that, this is just another renderings of that in 3D. This is the MATLAB design software from Mr. Desh. And now I'm going to go from nozzle design to test stand interface. There's still a lot of work to do here. We really did not get this done. But the purposes of your test stand interface: control the propellant feed, have temperature sensors, pressure sensors to stabilize the thruster so that when it pushes back, it doesn't move around. It needs to be able to track smoothly. And then we can have a load cell out here to measure the thrust. So that's what's going to have to go into that design. Here's controlling propellant feed. This is an example of a poppet valve. You can see here where it's going to be closing on this with this plunger. It's solenoid operated. And this was one that I was considering because it was very inexpensive. The only issue is I've not been able to prove to myself that we can take it apart and clean it and passivate it so that it can be used for peroxide. Because if we can't do that, we can't use it. Okay, then we're going to need temperature sensors put in various regions. Again, we do not know what temperature sensors we'll be using. They just have to be compatible with peroxide. And then pressure sensors, the same thing. And then I already talked about that. I don't want to stay here too long. We'll use a piezoelectric compression load cell to measure the thrust. We're looking for 15 newtons. So this is how we made these things. So we started out with our requirements. We were able to use Fusion 360, which you have had a workshop in how to use Fusion 360, giving you two-dimensional drawings, three-dimensional drawings, and then those could be converted to STL files, which can then be brought to software. This is your slicer software for your 3D printer. Cura is one of those possible options. It produces what's called G-code extension files. Those are given to a 3D printer, which is then going to make the plastic prototype, and then we can do a fit check, and then we're going to eventually do a flow test to see how that worked out. And so, and you guys already know about Fusion 360. I won't stay there. And then this is what we were getting from Fusion 360. So there's our catalyst pack part. There is our nozzle. We can put those together, get the entire thruster. And then these are the parameters we used in the slicer. And I'm not going to go through these really unless you have an interest in this. The one thing that we did play with is to make this a more robust. Okay, I have to look at this one. I talked about this previously. If you can see inside here, I ran out of plastic, so I was not able to print the outer screen of this, so you can sort of see what the infill looks like. And there's different choices you can use for infill. So this is a grid like what we have here. And the idea is the grid is only 10% of the volume inside, the other 90% is open. If you wanted to make this stronger, you could go with 40%, and you could change to a different infill pattern. And I wanted to play around with that. So this is the gyroid infill type thing. You can see how this is going to, these are going to connect with each other, transmitting the load in all three dimensions and making a much stronger part. So here's some pictures of what I've been showing you, the actual devices. So this was our fit test during first assembly, clearances between the pieces, and if there was any redesign before we actually make this into metal. And then this was our water test, which did not work, unfortunately. There's some of our different people. Amin did a lot of this work here. His brother, Muhammad, did a lot of work. Carlene and Paul, and there's other people that just were not in this picture. And after we did our water test, we were wondering why it leaked. We were able to find where the adhesive did not actually fill in, and that's why it leaked. Not anything real amazing there. And so what we have left to do is quite a bit. We want to model the flow and the physics using Fusion 360. We want to convert the catalyst pack into CNC files so that we can use computerized control machining, and we need mechanical drawings of this because the person that controls our access to the milling machines insists that she have mechanical drawings first. We're going to fabricate a catalyst pack from 316 stainless steel, design and construct our test dam, enrich 35% peroxide to 50, going up to 98%. We'll test the catalyst pack with those peroxides, compare the results to the physics model that we get in Fusion 360, possibly do a refinement of our model. We'll revisit the nozzle design using the data we get from the catalyst pack test, fabricate the nozzle, in other words, fabricate this from our stainless steel, model the flow and physics again, test the thruster with the nozzle this time, compare the results to the model, and produce hydrogen peroxide finally using the electrocatalytic method that we're proposing could be done on the moon and on Mars, and then test it with that peroxide. I know it's the same stuff, whether we buy it or whether we synthesize it, but people like it at NASA want to see us actually take it through the entire process. Now on the machining, the catalyst pack will be machined from this piece here. This is about 25 pounds. This is 1 foot in length. It won't be a foot, I don't know, it will be more like 4 inches. The bulkheads at the ends, in other words, these pieces will be fabricated from these pieces of stainless 316 metal. So I want to acknowledge our friends at SARC, and I'm sorry some of you folks that have joined with us later on, I don't have your names on here. I apologize for that. And then some references that we used in this. These will be available to you, and I believe this is the end. No, one more thing. Oh, is that the same? Oh, no, these are references. Okay, these are references specifically to our project at Triton and Fisk. And then these are references to hydrogen peroxide in general. And these, you can find these. They're not that hard to locate. And that's the end. So, are there any questions?
I'm sure there are a lot of them, Dr. Rudy.
Oh, I should stop you sharing too. Oh,
Yeah, no, it's all right. We can do that.
okay, already did it. Okay, or you did it for me, I think.
Thank you so much, Dr. Rudy, for the informative and educational talk. I'm sure the viewers gained a lot of knowledge about safer and greener alternatives to propellants in rocketry. Now we have with us one of the viewers, Siddhartha. He asked a question which was very interesting, and so we have him with us, and we'll add him in live, and then he can ask you the question directly, sir. Is that all right with you?
Oh, it's wonderful. Yes.
Yeah, sure. Siddhartha, you can go ahead.
Yeah, good evening, sir. Am I audible?
Hello.
Yeah, am I audible, sir?
I can hear you, but yes.
Yeah, sure, sir. So my question was, there was a recent chat going on about use of polymethyl methyl acrylate, PM, also known as PMMA, when burned with oxygen, is a kind of comes in a kind of green propellant. Is it a kind of green propellant or not? Because it produces a clean energy with carbon dioxide and carbon monoxide and water vapor. So
That would be fabulous, but I'm not. Unfortunately, I'm not familiar with it. The only other, ADN is the only thing I know of, and ADN does decompose to, I believe, nitrogen and water. and the issues with using ADN is the temperature. It's very difficult to have catalysts that can survive that high temperature. But can you put in the chat what that material is again, so I could see that, please?
Yeah, sure, sir. Yeah. It's a basic thing which we find in all the acrylic windows and all. We use this.
Oh, okay.
PMMA.
Yeah. So you can do a hybrid engine with that.
Yes, sir. So the solid part, which is PMMA, would be the outer shell, and the oxidizer would be the pure oxygen. So if we burn it, if we have the complete combustion, we could get a carbon dioxide, carbon monoxide, and water vapor. So my question was, can it be considered as a green propellant? Because there's a small amount of carbon monoxide which it produces, so which is a kind of concern to the environment. So can it be called?
Well, you remember I was talking about pseudo green. Anything that's not making water or making oxygen or nitrogen, then it's not totally green. Of course.
Yes.
So, but it's better than other things. Now the question is, does this? You said carbon monoxide, so it's obviously not completely combusting, and I'm wondering if it also produces particulate. So it may be producing particles of uncombusted material, and that's what you see when we would burn the solid rocket motors with the space shuttle. There'd be a lot of debris produced, and I think it might do that, but I don't know if they can get the combustion ratio correct, then it should burn hot enough to completely combust. But I really don't know, but I'll look into that and I can get back to you on that because that's quite interesting. We were going, we're wanting to do a peroxide kerosene thruster, but hybrid engines is another way to go, and not very difficult to do. If you want to have some fun, a do-it-yourself version of that sort of thing, if I can find something here that would be appropriate. Oh, this would work.
Yeah, I actually tested this PMMA with combusted the PMMA and made it to accelerate through a nozzle. But the only problem being in academics is that we couldn't achieve the pressure required, so much pressure required for the combustion. Only that couldn't be done, but we could get the what you said about this residues being coming out of incomplete combustion. We could collect those residues and see
you could do a plume you could do a plume analysis and see what you're having. Now, if you're working with some school children and you want to have some fun, you find a bottle about this size, and you put yeast and sugar and water in here. And so, no, that's not it. Oh, I'm sorry, I'm doing that wrong. Now I'm forgetting what you use. Hydrogen, that's it. Hydrogen peroxide. You can put hydrogen peroxide and low concentration peroxide, and basically you can take a piece of round pasta, like spaghetti, except the round stuff, the tube. You put it in the top. You have your little oxygen generator down here. You put a match on there, and you make a little rocket engine. It's really cool. Kids love that. That's fun. Anyway, that's not what you were asking me, but at any rate, I'll take a look at this. This sounds interesting. I have a friend, I've not seen him in a long time, that hybrid motors is all he does. He doesn't do anything else. That's all he's interested in, and he certainly would be a wealth of information on this. And so, and he would probably speak with you, I think. So,
Sure, sir. Yeah.
yeah, but he's at Marshall Space Flight Center.
Well, we'll wait for your answer, Dr. Rudy. And
Yeah,
thank you,
I'll
Siddhartha.
need to look at that some more.
Sure, sure. Thank you, Siddhartha. We'll also get back to you, Siddhartha. Yeah, Dr. Rudy will be with us, and we can maybe chat and explain the
Right.
answer in more detail. You can get
Yeah,
back with
sure.
us.
Yeah.
Thank
Yeah,
you.
yeah. Yeah, thank you, sir.
Mhm.
Now, Dr. Rudy, we also have some other people like Varna and Tanmay. They also want to ask questions. So
Okay.
I'll let Tanmay in. Hi, Tanmay.
Hi. So I actually wanted to know what are the different ways of that we can atomize the fuel while we're injecting it in the engine. And also, would you do, like in this case, when you're using the HTP as a bipropellant or as a monopropellant, would you do it before you inject, like before it catalyzes, or after after it interacts with the
Oh, it's
catalyst?
after. Oh, it's certainly after. You're bringing the peroxide into your catalyst pack, and then actually this one would be better. If you're bringing in your peroxide here, then your steam and your oxygen's coming out of here, and then if we inject our kerosene or whatever fuel we want to, then our combustion chamber would be here. And the way you would optimize the combustion ratio there, well, you would want it to be stoichiometric. So you would look to see, what would be the proper number of moles of it. But of course, it's a flow condition. So you would have to have, I think you would start with the flow of the oxygen and hydrogen, knowing what it is, and then you would adjust the fuel to that. And I believe what has been done is you start one of those with only peroxide. So you're making oxygen and steam, no fuel. You turn on the fuel a little at a time. You start bringing that up. And then you can tell by the characterization of the flame whether you're achieving, it's just like adjusting a Bunsen burner, where you're adjusting that burn ratio. And that would be, I think, probably the approach that would be taken. But you could calculate it in advance and know what it ought to be. Because it's a flow condition, it's a little more challenging, although, of course, we can model flow conditions in something like Fusion 360. I don't know how to do it, but I know you can do it. So I think from an experimental approach, though, I would just start making oxygen and then start introducing fuel, and then you can see, is it lean or is it rich? And you just, it's going to start out lean, and you bring it up until it starts to become rich, and then you would bring it back from that, from an experimental way of doing it. I think you can use the color of the plume to do that.
I hope, Tanmay, your question was answered.
Yeah.
Thank you.
Thank you.
Now, I also have Varna. She has a question for you. Here you go, Varna.
Okay.
Hi, good evening. Okay, I know that green propulsion must have numerous advantages, but are there any limitations to green propulsion? Any disadvantage or any sort of challenge?
Okay, I understood the last part. Is there an advantage? But I couldn't catch what we were concerned with.
What is the major limitation of green propulsion?
Major? I'm sorry. How about putting it in the chat? Maybe I'll get it there.
Yeah.
Thank you. Oh. It's going to be performance, of course. You're going to be sacrificing performance. You remember when we were looking at the numbers, if you can use hydrogen and oxygen, of course, the performance is fabulous. But then you have some limitations there because of the density issues, and you wind up with a very large tank. Like on the space shuttle, the tank was very large, causing a lot of resistance on your initial launch, and so you're expending fuel needlessly, propellant needlessly, because of that large frontal area. And if you can get a higher density fuel, then you're going to be much better. And that's why SpaceX is using kerosene and LOX, I think. That's my assumption. That's why they're doing it. So, but the limitation in using green generally is not as good performance. But with hydrogen oxygen, your performance is good, but you've got some other issues.
Thank you.
You're welcome.
It is such a pleasure having you here today, Dr. Rudy. There were not many other questions who could come live with us today, but
Okay.
Karan Singh was asking about black box MATLAB application that you mentioned in your presentation. Do you have?
Okay, that's used for designing a nozzle.
Okay.
And Vinayak, that wrote this, the MATLAB application, you're supposed to be able to put in your chamber pressure and what's going to be the pressure that you're operating in. Are you operating in vacuum or at sea level? And some other parameters that I don't recall right now. And it should give you the two-dimensional half of the profile of the nozzle. And then you can then put that into Fusion 360, do a rotation around that, and produce the 3D object. We could not get it to work. What we were getting is either only the diverging or the converging portion, but not both. And I don't know why. And we were going to ask him about it. And when I first was talking to him, he had quite a bit of time because he's in school in Montreal. And then he got busy with his thesis and he was no longer available, and I've not tried to talk to him again. So there's some issues there. So the gentleman at Fisk University, he went to first principles and did the calculations. But I realized that we don't really know the chamber pressure. So we're designing to something that we don't know. We're estimating what it is based on what other people have found in building their thrusters. That doesn't mean our thruster would be the same. So that's why we need to build our thruster, and we need to test it and see what the chamber pressure actually is, where it's coming out, so that we can then design to that and not design to some theoretical number.
Correct. Okay, I think, Karan, your question was answered. I hope our listeners learned from you, Dr. Rudy. If you guys did, can you share some appreciation for Dr. Rudy, or maybe just say yes that you guys did?
That part's not necessary. Now with Vinayak Desh, you can find him. He's on Snapchat. I think no, not Snapchat. The other thing. What all the cool kids are doing. What's the other?
Instagram.
Yes, Instagram. Yes, he's on there. If he's not busy, he'll talk to you. I'm making a major assumption here from his name. I'm assuming he's from India. He might be from your neighbors from the north, in which case I don't guess he's going to speak with you. I don't know. I don't really know your politics.
We'll try to find him.
All that. I don't know what's going on there for sure. I confess ignorance of really knowing what it's like. So, but you guys know what's going on. So you should be able to find him.
We'll try to find him.
Yes. He does a lot of interesting things.
And his connection.
He explains.
Yeah, Karan Singh is saying his.
He explains how SpaceX is doing their vertical landings, and how you would control a rocket to do that. He's figured that out. He talks about how to do a autonomous self-driving automobile. So for your computer science people there, I think you would find some of his videos very interesting. He's on YouTube, and he has some really interesting stuff. pretty
Okay.
diversified.
Dr. Rudy, we do not have any other doubts today.
Okay,
With them, I
fabulous.
think, yeah, the session went very well. Thank you for being there with us. Varna.
Okay, and you're going to be talking about structures tomorrow, correct?
Yes,
Okay, very good.
vertical structures. We have had 3 successful sessions by now, and 3 more are left. Let's see. Well,
And
Mr. Babu, something to
I,
say?
I have a proposition for you folks to be thinking about, and that is Fisk and Triton will be entering the Space Launch Initiative competition again, and I am going to see if we could include you in our team. I don't know what NASA will say of that, but I'm going to ask and see what happens. If you're interested in doing it, I think you probably will be. And we could then do the same things in both locations. It would be a very interesting thing to try.
Sure, Dr. Rudy, we'll look into it.
Okay.
We'll never say no to an opportunity.
That's right. I don't either.
Okay. Space. Varna.
Thank you, audience, for joining us today. And we will be conducting an interactive session on avionics basics tomorrow. So do remember to join us tomorrow at the same time. My sincere gratitude to all of you who joined to make this event successful. Thank you.
Thank you, Dr. Rudy. I think you also might have your day ahead left with you. A lot of work to do. We are now 10 in the evening.
My daughter and son-in-law are visiting me, so I'm going to be seeing them. So I'll be busy with that.
Well,
But you have a good evening there and be safe.
thank you.
You too. Thank you.
Bye now.